Hello and welcome to episode number 327 of the Armin Show podcast. Welcome to 2022. Subscribe if you haven't. Listen in. We can always learn more. On this one here, we have the author of this book. What a cool cover. Life is Simple. How Occam's Razor sets science free and shapes the universe. We'll be talking about that. And also with the professor, Johnjoe McFadden of the University of Surrey, professor of molecular genetics. Welcome to the show.
Thank you, Armin. It's a pleasure to be here.
I'm glad to have you on. I like the cover, by the way. Sometimes covers of books are more standout than others, and this is one that is that.
Good.
It's a cool feature. Now, before we go into the book, you're at the University of Surrey studying molecular genetics. How did you get towards that? Why science? Does anything in your personality connect to where you currently are?
Why science goes back to school days when I was studying a range of subjects, as everyone does, and as a young teenager, like all young teenagers, being confused by the entire world that is presented to you at the time. And one of my teachers, who I remember well, Mr. Pescott, unveiled the periodic table. And I'd done a little bit of work on chemistry before then, but it all seemed confusing. There was no order there. It was acids do this and alkalis do this and oxidizing substances do this and that. And suddenly there was a system which made order, made structure, and you could predict what an element was going to be like, but just by knowing where it was in the table. And I thought, wow, that's great. That's a way of making sense of the world. And that's what's always driven me in my interest in science, making sense of the world. And that's what really brought me to Occam's Razor. It's a good way of making sense of the world.
This is true. Simplicity is key. And there seems to be a theme that breaking things down to the simple had to be the way. There was no other choice along the way. What is Occam's Razor for people who would like to know?
Yeah, so Occam's Razor is the principle that if you're given a number of possible explanations of anything, how the stars move in the sky to, what's caused COVID, then you should choose the simplest. And although you said there wasn't an alternative, in fact, where this came up first, it was in the medieval world, really, and there was lots of alternatives. The standard explanation of if you saw something moving in the sky was, well, it must be an angel pushing it, or a demon, or a god, or something. And this was how everything was explained. Instead of trying to pin down the number of entities that there were in the world, if there was a mystery, where do the winds come from? Well, it must be some supernatural force pushing them. Where does disease come from? It must be caused by a bad spirit that enters your body. So for every phenomenon, the approach was really, well, let's just invent something. And William of Occam, who was a medieval friar, a Franciscan friar in the 13th, 14th century, was the first to really go against this grain and say, no, we should try to make sense of the world with the smallest number of parts, if you like. And what he said was, he said it in a number of ways, but probably the way that Occam's Razor is best known is entities should not be multiplied beyond necessity. And by entities, he meant things that exist, like angels and demons and planets and stars and wind and rain and all of these things. There's a certain number of them that we have to use to make sense of the world, like rain definitely exists, and many that don't. And what William of Occam said is get rid of those that don't. And he also said that, you should keep your explanations simple. And, if there's lots of explanations for something, choose the simplest. And this is what we know as Occam's Razor, that we should take the simplest arguments, simplest theories, simplest explanations. And this is what Occam's Razor continues to urge us to do.
Mm-hmm. I like how you presented it. Also, you presented how future people took that concept and they were like the philosopher that connected with that. And then the next one. I noticed that in certain concepts, people take the story and run with it.
Absolutely. Occam's is a little bit hard to trace because we were with Occam when he came up with this notion of taking the simplest. And one of the things he applied it to was proofs of God. And these had been devised, most of them had been devised a century or so earlier by Thomas Aquinas, who provided 5 proofs of God based on Aristotle's logic. And Occam just took them apart and said, no, you can't, none of these work. And he used his razor to eliminate lots of stuff that was in the medieval metaphysics, as it's called, the metaphysical universe that philosophers worked with then, and said, no, this doesn't exist, that doesn't exist. And removing a lot of them also undermined some of the notions of the Western Christian religion at the time. And so he was accused of heresy and was excommunicated. So it meant that future scholars who referred to him, who should have referred to him, often didn't, because he was a highly controversial figure, an excommunicant, and that made tracing the path of his reasoning is tricky, but it's picked up by scholars like Copernicus, who similarly looked for simple solutions to the motions in the heavens, and people like Newton, who looked for simple laws. It was really the defining feature of all of the great scientists that they looked for simpler ways of making sense of the world and found them. And this is what we call modern science. It's basically the simplest way we can account for the largest number of phenomena.
Right. Would you say that Occam's razor is somewhat connected with deconstruction, breaking things down to their base, or not exactly?
Yeah, it is. It is in a way. It's kind of saying, okay, well, when I talk about, you can talk about things like forces, say, in physics. What do we mean by a force? What Occam's razor forces you to do is say, okay, what's this thing force? You can't just say it's there because it's just a word. Okay, you've got to define it in some way. What is it? It's when you infer its presence when something moves. So how do you know it's moving? And it forces you to go on and kind of doubt everything until you come to the hard kernels of our world that definitely exist. And you find on the way that things like velocity, for example, don't necessarily exist because they only exist in some frames and not others. And it forces you to kind of drill down to find, okay, what's the minimum number of stuff? It's the kind of thing that, of course, Descartes was famous for, in saying, his philosophy started with, I'll doubt everything. And ending up with, I think, that therefore I am. And he couldn't doubt himself. Occam's razor urged people to do that several centuries earlier by just saying, yes, you need to doubt everything. And when you've come to the rump of stuff that you can't doubt, that's what you have to work with. And that's really what science is based on, finding the ultimate realities that we have to deal with, and not inventing stuff.
I like this concept in personal life as well. When you have things boiled down to the simplest for yourself, suddenly you have like your base values or core or thoughts that you can take for 30, 40, 50 years, and they'll always ground you. But if you don't have those, you may be more shaky over time. One thing that come to
carry on.
Sorry, was I like the example that you brought of the solar system and how the view from not the Earth, and then the view from the Earth, and how they were compared, and how simple it became when looked at from a different angle. Can you speak on that concept?
Yeah, sure. So the first thing is, I always like to remind myself and tell people that the people who had these, what we would call erroneous ideas, weren't stupid. They were making sense of the world in the best way they can. So, for example, they looked up in the sky during the day, and the sun seems to be appearing rising in the east and coming around the sky and descending into the west. Earth seems to be still, the sun seems to be moving. And that happens every day. Similarly, the moon and all the stars at night do the same kind of thing, only they rotate around the North Star. So, and yet the Earth seems still. So it's obviously that what you're going to do is try to make a model, first of all, in which the Earth is still and everything else moves. But it was when that was done, and the last great astronomer of the ancient world, Claudius Ptolemy, came up with a model of how everything was moving in the heavens. And it was geocentric, the Earth was still, it didn't even spin. And he came up with this model, but it was very, very complicated. And Copernicus, when he came to look at it and try to make sense of this, he called it monstrous, the complexity of it. And he then, actually, it had been suggested 200 years earlier by an Occamist scholar called Jean Buridan, that we ought to, first of all, try to make a bit better sense of it by saying, instead of all these objects turning around the Earth every day, why don't we allow the Earth to turn and keep them still? And suddenly you get a great simplification in that everything is not moving around the Earth every day. And then with this great simplification that was first proposed in the medieval world with Jean Buridan, who was an Occamist scholar, picked up by Copernicus, that was the first move. He allowed the Earth to spin. And then a lot of the motions in the heavens were stilled. And from that, he could see that there was a simpler solution even than this. And that was by putting the center of the motions not where we're sitting, but somewhere else where the sun sits. And then if you did that, you got an even simpler system. And his only justification for this simpler heliocentric system with the sun in the center was that it was simpler. That was the only justification, because in fact, it was no better at making predictions of the motions in the heaven than Ptolemy's geocentric system. So Copernicus's only argument was that it was simpler. And that was picked up by other scholars like Kepler, who actually found a greater simplification. You could replace all of the orbits by 3 laws of orbital motion. And that makes it even simpler still, because you could apply them to an asteroid, even though they weren't known at the time, traveling around the sun, or spaceships or anything. It's a simple set of laws that apply to all of the objects. And then, of course, Newton came along and said, well, scrap Kepler's laws. They all follow from my even simpler set of laws, his laws of motion and laws of gravity, which account for motions not only in the heavens, but now down on Earth as well. And he could throw those laws into he couldn't, but we can throw those laws into the kind of objects that the new James Webb telescope will be seeing in the far distant reaches of the universe. And we'll expect them to abide by those same laws that Newton discovered from apples falling on trees and from stars moving in the heavens. That same set of laws, applying as far as we can see it, is an extraordinary simplification that isn't guaranteed at all that the universe will be the same everywhere. So far it seems to be. And that makes our job of making sense of it much easier.
This is likable for the average individual, because then the world shouldn't be so complex at all parts. Obviously, things have fallen into some form of stability, and we see it. It's not like everything's breaking down in one moment, and we can see far beyond our Earth smoothly. And so if there was so much complexity, it wouldn't be more straightforward. We wouldn't have we have like a reduced entropy of some form, and it is able to be taken in. So a complex explanation seems like excess.
Yeah, absolutely. And this is what Occam, William of Occam urged us to get rid of the excess. If you can find some simpler way of making sense of the world, then you should do so. And the great scientists like Copernicus, like Kepler, like Newton, like Einstein, they went along that path and made the world simpler. Even though general relativity doesn't seem simple, or later quantum mechanics doesn't seem simple. But if you try to make sense of the phenomena like black holes without general relativity, if you try to make sense of them in Newtonian mechanics, you can't. So it's as simple as you can do. And it still means that sometimes the laws seem, from our perspective, to be very, very complicated and hard to understand, particularly by non-physicists like myself. But it's usually a question of perspective and what very brilliant mathematicians and physicists are able to see is that, say, the laws of quantum mechanics or the laws of general relativity are beautifully simple, but in a way that's kind of like you have to shift your frame from being on the Earth to being in some mathematical space, equivalent to seeing the, shifting from the geocentric to the heliocentric perspective, but now you're doing it in a mental frame. And if you, as a physicist or a mathematician, you get into that mental frame, you can see that beautiful simplicity that Einstein saw in the general laws of general relativity laws, or quantum physicists see in Schrödinger's equation. So the simplicity is there, but it's not always accessible to everyone.
It doesn't need to be hard. It's a different view of perspective of sorts.
Yeah.
One thing I like in the book is that you have, well, I see it like two threads. There's the science and the scientists across the way, and then there's the philosophers along the way at the same time. I really like philosophers in Wittgenstein and Aquinas and others, so I resonate with that quite a bit. How important are both paired over time? Does one guide the other? How would you relate to philosophy and
early on in Occam's time and through people like Copernicus and Newton, etc., science was really a branch of philosophy, and they were called natural philosophers. So philosophy and science went hand in hand, and the philosophers in even Robert Boyle's time at he was a scientist who's often thought of as the father of chemistry. He had many disputes with philosophers over what his chemical experiments were about. We don't tend to have those these days, and I think that's a great shame, because I think there is a tendency for us scientists to just kind of do the sums, do the experiments, and just go on with it. But for me, at least, it's always the big questions are always the most interesting ones, and what they tell us about that. And we need philosophy to make sense of that. What is the ultimate reality? What is science all about, and where is it going? And I think to me, it's fascinating. And this is in my book. I do follow the philosophical threads as well, and to me, they're just as important as the scientific ones. But the scientific ones have more practical value because they send spaceships to Mars or make our laptops work and that kind of thing, whereas philosophy doesn't have so many applications. But in terms of their value to human thought, I think it's they're equally important.
Mm-hmm. One thing I think about is, so Occam's Razor was recognized at some point. When were there any certain points where it was battled against? Other people had like a alternate view toward it, and were thinking that complex was more the way. Has there been any sort of dispute of it?
Yeah, there's been loads of them. I mean, in the early history of chemistry, there were things like phlogiston, which was a substance that was supposed to transfer heat from one place to another. It was eliminated by an Occamist kind of, well, you don't need it anymore, when thermodynamics became apparent. And similarly in say in biology, a lot of people still argue around the world for creation being how life appeared on Earth. So instead of how many species do we have, something like so many millions of species, they were each individually created by a divine being who we call God. And that's a great complexity compared to how biologists view life on Earth, that it's a simple beginning. We don't quite know what it was, but it was a simple beginning of a single bacterium-like organism. And then everything else followed from the extraordinarily simple principle of natural selection and evolution, that once objects are inheriting material but making mistakes, mutations, then automatically natural selection kicks in and organisms get better at what they're doing. And this is what's happened over billions of years to take us to the vastly diverse and fascinating biosphere that we see around us today. It doesn't require millions of individual creations, just a single emergence of a self-replicating organism so many billions of years ago, and the laws of natural selection, and you're away. You explain the biosphere. So, but that is still resisted by many people who prefer to have the divine explanation for the biosphere. So there are still conflicts, and in all spheres. In my own sphere, I became interested in this because of my own work is in an area called systems biology, where we use mathematical models to try to work out what is going on in biological systems. As you know, with the genome sequencing project, first in humans and then in lots of other organisms, there's a huge amount of data out there. We know so much about, the number of genes. I study bacteria, and they have a few thousand genes. And when we try to make sense of the data that we get when we do experiments, we try to build models. And then the question is, how complex should we build those models? Should they be as simple as we can make them, such as Occam's Razor might insist or suggest, or should we make them as complicated as we know the organism is? 3,000 different genes. And this is how I got into it, because I was having a discussion and a dispute with a colleague, Hans Vesterhoff, a colleague and friend of mine, who believed in that we have to put everything into our models, because only then will it be truly inclusive, and we only then will be able to pick up these higher level systems properties, the emergent properties. And whereas I resisted that, partly because we can't, they're just too complicated, too unwieldy if you throw everything in. But also I think you have to stick to the principle that you should only put in what you need to explain your data. So my principle was, and continues, that when you try to account for an experiment, you don't throw all 3,000 genes at it. You said, okay, what's the minimum number of genes I need to account for this experiment to make sense of it? Because we don't know whether they're all active. And if we just throw them all at the system, all at the data, then we'll tend to just get the noise, the experimental noise, filling up all the parameters, and we'll get stuff that just doesn't make any sense anymore, because actually we're fitting parameters to noise rather than real data. What Occam's Razor urges you to do is, okay, we know there are 3,000 genes and they may be involved, but let's find out what the minimum is that we need to account for this data. We'll start off with that. And when you tell me I need to have another gene, I'll add it. But until then, I'm going to keep it simple.
It's sort of like nature in a way, because that's what it has to do, or had to do over time. Keep it to the basic. Any extra body parts or weight or anything was more risk for not living or not propagating to the next generation. So everything whittled down to like the perfect element.
Absolutely. In our early embryo, we have a tail, and it gets absorbed because we don't need that tail. Our appendix was used at one time as it does as it's in other animals such as herbivores, but we don't graze on grass and stuff like that anymore, so we don't need it. So there is this tendency in evolution to get rid of stuff, which happens kind of accidentally, because if you don't have a selective pressure to maintain something, then mutations will kind of lose it. And this was shown, as I described in the book, in the naked mole rat, which is an organism that was a rodent that is naked. It doesn't have any fur, and it lives entirely underground. It has eyes, but they're blind now because it's been living underground for many, many generations. And mutations that took place that normally would not survive, an animal that becomes blind on the surface would soon die. They'd be eaten by predators. But because there's no predators under the ground, it didn't need mutations that lost sight weren't selected against. So now it's lost its sight because of its genes involved in sight being mutated. That happens to anything that becomes superfluous in our genetic makeup. Mutations take over and make it no longer functional. So we are lean and mean. What we have, we tend to need. There are a few exceptions to that. We males have nipples. We don't need them. We don't suckle young. So there may be reasons for keeping things, like it may be easier developmentally to have the male body pattern, including nipples, rather than having it working on a different body plan. So there may be exceptions, but by and large, everything we have, we need. And if we didn't, we would have lost it, like our tails.
This is a great thing about reality. I like this concept in the bigger picture because the unnecessary is supposed to be removed out. Reality always takes care of itself over time. And also, even with people, if someone is more presentational or bringing much more than seems to be a default, it's usually more of a manipulation than an actual item, because those who have the most actual internal keep things the most light and communicative, and are able to share because they're not adding extra layers of fabric on top of it.
Mm-hmm.
Now, one thing I wanted to check is, what is the most recent example or recent examples of Occam's razor applying in science?
The first thing I should point out is scientists use it all the time, and they don't realize it, but they do. If you ask a scientist, would you, if you do an experiment and you get some result and you have two possible explanations, one's simple and one's more complicated, and you ask a scientist which you would choose, they may hesitate for a while. They might kind of say, "No, are you sure? Are you sure that the simple one accounts for all my data?" And you say, "Yes, all your data, and it accounts for all this stuff, other stuff that I know as well that's in the background. Yes, it accounts for all of that." Then a scientist would always say, "Yeah, okay, I have to adopt the simplest solution." No other way of making sense of the world has that criterion, that if you don't need it, you drop it. It's not in religion, it's not in philosophy, it's not in art. You can have as much superfluous stuff as you like. But given a set of some data from an experiment, then all scientists will opt for the simplest solution. So it's used all the time. Every time you interpret an experiment, you interpret it in the way, if you're a scientist, you always interpret it in the simplest way. That's kind of part of the training, but it's become invisible because we do it automatically. But there are times when there are really key moments, like discovery of the Higgs boson. Now, when Higgs proposed the Higgs boson, he could have proposed 1, 2, 3, 4, 5, 6, 7, as many as you like. There's nothing in the theory which which fixes the number of Higgs bosons. And what Higgs said, well, the simplest is one Higgs boson. And so far, that seems to be the case. We've only found one Higgs boson. That's all you need to, if you like, fix the problem that the Higgs boson fixed in particle physics. And one was needed, one was found.
I like the comparison between science and the other categories. They have more room for floweriness or things that give art or joy or some spirit to life.
And absolutely, there's no problem in outside science of being extravagant with the number of parts of systems. Although I think still in our personal life, I think we should try to, we can have as many pretty pictures on our wall as we like and be as complicated as we like. But when we try to make sense of the world around us, even outside of science, it's best to use the simplest solutions. And I think a lot of the issues we're having at the moment in pseudoscience and conspiracy theories and stuff like this is down to people not using Occam's razor and just accepting stuff that there is no foundation for.
It's a great point. Actually, that would counter a bit of the rhetoric or cause of polarization. If there's a rule that when you present things, they have to be, one step at a time, not like 14 things tossed in together as a package and supposed to convince the listener.
Yeah. I mean, one of the other directions that I came to Occam's razor was when I was kind of shocked when I met actually in the US and happened to be at a meeting and there was a creationist there. And I always thought I could easily dismiss all the creationist arguments, this fossils and stuff like this. I know this stuff, I can defeat them. But in fact, I couldn't, because I would mention fossils and this guy would say, well, that's just, the creatures that lived before Noah's flood. And I would say, well, okay. Well, how is it that they have these theories in the geological record where fossils gradually change from one thing to another as you go up the rocks, and what he said, well, that's caused by hydraulic sorting of different animals when they died in the Noah's flood. I was, okay. Well, what about the fact that when you say this Noah's flood happened, that explains all this kind of stuff. It was only something like 2,000 or 3,000 years BC. And the pyramids were built around then. I mean, wouldn't the pyramid builders have noticed that their pyramids are underwater for a mile of water for several years? Wouldn't they have noticed this and kind of recorded it in their hieroglyphics? And the explanation for that was why you don't really believe the dating of ancient Egypt, do you? In fact, it happened much later. And it goes on like that. Everything you throw at them, they have an explanation. But it kind of builds this crazy edifice of unsupported premises, like, that there was a flood, there's no evidence for this great flood, and this hydraulic sorting, there's no evidence for that. They pile them on top of each other. So at the end, you just have this huge pyramid of explanations that become more and more unlikely. But that doesn't matter. As long as it struck me that you can probably never disprove anything. And I think that's true, that if you have a sufficiently clever person who would find, is the world flat, that finds some way of saying, well, actually, all of those pictures are taken from outer space are all fraudulent, there's no curvature on the Earth because of some optical illusion and something. They would find some way of making sense of it, but it would be an extremely complicated way. And what Occam's Razor has said, get rid of those complicated explanations, choose the simplest. And I think that's the way we have to deal with everything in the world. When we're trying to make sense of the world, rather than trying to decorate it with, great music or great art and stuff, make them as complex as you like. But if we want to make sense of it, stick to simplicity.
I like this in relation to something I've mentioned about lowering friction, making such a complicated scenario. I feel like it takes a lot of, let's say, glucose in the prefrontal cortex to come up with all the concepts. And there's like a friction there because I have to figure out this, but this. Whereas the other person is, well, this occurred. We have this record. It's more light natured. And you don't want to go towards where there's friction because you wouldn't drive a car where the gears were grinding too much. That wouldn't be good.
Yeah. Mm-hmm.
Now, in the science category, who are some scientists of the current time that you like or read their works or base your work off of?
It depends on what you mean by work. In terms of my professional work, which is what I do, I work in microbial genetics, and that's based on the work of many scientists. My colleague who I mentioned before, Hans Westerhoff, works in systems biology, and some of my work is based on many of the things he did. There are too many scientists to mention, and that's the thing about science. There's so many scientists who have contributed to it over the years, and all of them, mentioning one or two is kind of irrelevant because it's hundreds. So, which scientists I admire today? The scientists who have, I suppose, made the COVID vaccine so quickly is certainly one of the most impressive achievements in recent years, that they came up with a vaccine within months of this virus being discovered. That's an extremely impressive achievement. So those are the kind of people I think who right now come to mind in terms of the, and there were many of them then because there are many different vaccines that have been made by different teams, but they all start with the premise of let's make the simplest one that works.
That's true. There were so many teams at the same time, and then they had a base from 10 years ago's research. That's kind of cool.
Yeah.
What would you, if you had a megaphone to the planet, what would be a message you would tell them all about your book that you would want them to take away for themselves?
Keep it simple. When dealing with the world, try to keep things simple. Don't invent stuff. Try to make our world as simple and therefore rational. This is what you get when you deal with simplicity. You get down to reason, and too much of human interactions are based on logic and beliefs that there is no foundation for. Take the simplest and you're on firmer foundations.
Keep it simple. This is the book, Life is Simple. Professor Johnjoe McFadden, I would like to thank you for having come on to the show and informed us all about Occam's Razor and more.
Thank you, Armin. It's been a pleasure. And thank you to all your listeners.
Glad for it. And we are out.